Hi, my name is Thomas Carr, and I'm a graduate student at the University of Washington. And this is going to be an online course in linear algebra. So, like calculus, I'd say that linear algebra is one of those really foundational subjects on which a lot of other subjects are built upon. And so, for example, let's say that you're studying science or engineering, virtually any kind of science or engineering. Then I predict at some point in your study, you're going to reach a point where, in order to progress further, you're going to want to learn some linear algebra. Let me see if I can actually show you an example of that. So let's say you're studying physics and you want to learn some quantum mechanics. So here's a book I have on my shelf. This is a popular quantum mechanics book by David Griffiths. And, I'm almost flipped to any page. Let's say this page here. And immediately we start seeing matrices. We start seeing determinants. We're looking at eigenvectors and eigenvalues of H, which I suppose is a Hamiltonian, which is a linear operator. So you can see there's just linear algebra all over the place. And if you try to learn quantum mechanics without linear algebra, it's basically going to be impossible. You might understand something here and there, but linear algebra is sort of one of the things that sort of makes everything cohesive. Okay, and we're going to talk about all these things in class, like eigenvectors, eigenvalues, determinants, etc. And so the point is that linear algebra is really your entry ticket to the higher level subjects in your field. This goes for a wide variety of fields. Okay, so that's why you might want to study linear algebra. What is linear algebra? What is linear algebra? Okay. Well, okay, so first of all, a big part of linear algebra is something that you've been doing for a while probably, which is solving systems of linear equations. Okay. Okay. And I think a lot of people would tell you that's actually the main part of linear algebra. It's not necessarily all of linear algebra. So in general, I would say that linear algebra is. So in general, it's the study of linear transformations. Linear transformations of vector spaces. Okay, let me underline these two words. Linear transformations of vector spaces. Okay, and already I put down two terms that you probably that you might not be familiar with. And it turns out this first one is actually a special case of the second one. So we can view a system of linear equations as a linear transformation on vector spaces. But one of the things we're also going to do along the way is we're going to learn sort of the vocabulary of linear algebra. Linear algebra has a language of its own. You can see that already. And so we're going to learn to also speak the language of linear algebra. Linear algebra has a very different character than calculus, I'd say. But for now, let's focus on this first part, just solving systems of linear equations. So let's do a first example. Let's do a problem that you've probably been doing for quite a while. So let's solve the system of equations. Okay, first equation will be x minus 2y equals 4. So we have two variables. And the second equation will be 3x plus y equals 5. Okay. So it's two equations and two unknowns. These are linear equations. There's nothing like an x squared or an x times y. The variables just occur as a part of a sum, and we have coefficients, maybe that we're multiplying them by. For example, this -2. Okay, what do we mean by solve the system? Okay, so let's be clear on what we mean by that. So meaning, oh, what do we want to do? We want to find the values of x and y. So find values of x and y. X and y are just standing in for numbers. That satisfy not just one equation, but both equations simultaneously. Okay. There are infinitely many solutions of this first equation. You can actually pick any value you want for x, and then you can solve for y. But we actually need a value of x and y that satisfy both simultaneously. Okay. And you might have already solved this one, like while I was talking just now. But there are several methods to do it. One is the substitution method. We could solve for x, for example. X equals 2y plus 4. Plug that in for x in the second one, and then solve for y. And then there's also a so-called elimination method. That's the one I actually want to talk about, because it turns out the elimination method generalizes more easily when we have more equations and more variables. So this is the elimination method. So in this case, what we want to do is we want to eliminate one of the variables. So eliminate. Let's say we want to eliminate x. Okay, so we want to eliminate this variable x in the second equation. And how do we do it? Well, what we're going to do is we're going to subtract or add, in this case, maybe subtract, by subtracting an appropriate multiple of the first equation. Okay, so what do I mean? Well, let's take the first equation, and we're going to multiply it by, what should we multiply it by? If we want to get rid of that x in the second equation, I think we should multiply it by 3. So we're going to have 3x minus 6y equals 4 times 3 is 12. So this is just times 3, right? Times 3. Now, what am I going to do with this? I'm going to take our second equation here, and I'm going to subtract this one. 6y equals 12. That's the same as adding a negative, so maybe I'll do plus minus 3x plus 6y equals negative 12. I'm going to add these two equations. Why can I do that, by the way? Why can I add this equation to that equation and still end up with something relevant? Right? Well, it's because I'm actually adding the same number to both sides. Right? This is the same as that. That's what this equation is telling me. So you can always add the same thing to both sides of an equation. And I get 0x, right? So I won't even write anything there. And I have y plus 6y equals 7y. And what do I get over here? I get minus 7. Okay, I'm just going to write out my system once more, but I'm going to replace the second equation with the 7y minus equals negative 7. So there's my new system. Okay, what do I do now? Well, it's pretty clear, right? So y equals negative 1. I can immediately see that from the second equation. I eliminated the x, and then x equals, well, x equals 4 plus 2y, but y is negative 1, so it's 4 minus 2, which is 2. So my solution is, let's write it like this. X comma y equals, x is 2 and y is negative 1. So here's my solution. Okay, so this linear system has a solution. It has a unique solution, and that solution is 2 comma negative 1. But we can immediately start to ask ourselves, so actually a few questions maybe. So let's say guiding questions. These are questions that we're going to be thinking about for much of the term. Okay. So given a system of linear equations, first of all, are there solutions? Okay. In this case, there were. If there are solutions, so if so, how many? And finally, how do we find them? Or, I mean, maybe we can't find them. Maybe there are infinitely many, so we can't just list them, but maybe we can describe them in a certain way. So let's say, yeah, how can we describe the solutions? Algebraically or geometrically. Okay. Let's look at a couple more examples of systems of two equations and two variables, just to see what other possibilities there are. So let's do an example where we actually have infinitely many solutions. So let's solve the system. Negative x plus 2y equals 2, and 3x minus 6y equals negative 6. Okay. Well, what do you notice about this? How did I get the second equation? I just multiplied the first one by negative 3. Right? So it's actually just the same. Well, it's not the same equation necessarily, but these represent the same geometric object in a way. Let's try to follow exactly the same plan as before. So we're going to try to eliminate that 3 right there. So I'm actually going to take my first equation. Or not eliminate the 3, but eliminate the x. So I'm going to take my first equation. Again, the thing I want to multiply it by is 3. And I get minus 3x plus 6y equals 6. Let's take that one, add it to the second one, and here's my new system. First one stays the same. I'm adding this to the second one, and the x's cancel, so I'll just get nothing there. But now I have 6y minus 6y. This becomes a 0y. That didn't happen in the first one. And what do I get on this side? Remember, I'm adding this one to that one. I get a 0. So 0y equals 0 is my second equation. What does that tell me? This actually tells me that y can be any number. Or at least looking just at the second equation. Yeah, y can be any number. Okay. And then when I put that number in the first equation, that tells me what x is. So often what you want to do is describe the solutions parametrically. So let's say y is any number. I'll call it t. So t is any number. Well, then what is x? X is... See, so we get x is 2y minus 2. So x is going to be 2t minus 2. Okay, so we can describe all the solutions with the parameter t. And if we write it in the same form as before, we have x comma y is 2t minus 2 comma t, where t, what is t? T can actually be any number. T is any number. So in example 2, we actually have infinitely many solutions because we can pick any value of t. Let's do one more example just to show the final possibility. Let's do 2x minus y equals 4, and 2x. Let's do 2x minus y equals 5. Okay. Well, if we try the same idea, let's take our second equation. and we're going to add or subtract an appropriate multiple to the first one. Let's just subtract the first one exactly. And we get, so here's my first one. I'm just going to write it again. I'm going to take my second equation, subtract the first equation. I get 0x. The x's go away. That's what we wanted. But I also get 0y. And on this side, I have 5 minus 4 is 1. So I get 0y equals 1. Well, is that possible? Is there a value of y that when you multiply it by 0, you get 1? Of course not, right? Because 0 times anything is 0. So this actually has no solutions. Okay. And these are really the only three possibilities, at least in this case, with 2 equations, 2 unknowns. And in fact, in general, the only possibilities we can get are 1 solution, no solutions, or infinitely many solutions. Although there are actually, it turns out there are many ways that we can get infinitely many solutions or no solutions when we move to higher numbers of variables. So that's what we're going to talk about next. But before we do, I just want to define some terms. So linear system is a definition. I'm just going to define some terms. So a linear system is called consistent. Consistent if it has at least 1 solution. So if it's possible to solve it, then it's called consistent. Okay. Otherwise, it is inconsistent. Okay. So this one here is consistent. We had 1 solution. This one here is also consistent. We have a solution. In fact, we have infinitely many solutions. However, example 3 is inconsistent, okay, because we have no solutions. We got a contradiction here. It's not possible to find a value of y that satisfies this. Okay. Let's look at the geometry. So what's going on geometrically here? This is something else that you're probably familiar with. So the solution, I mean, what do one of these equations by itself look like? So the solution set to, say ax plus by equals c. What is this? It's a line, right? What dimensional space does that line live in? We have 2 variables, so it's a line in 2-dimensional space. Okay. Okay. So each of these are lines. That's a line. That's a line. What does it mean to solve the system geometrically? So the solution to a system of such equations is the intersection of the lines. Of the corresponding lines, right? Why the intersection is because the solution to the system needs to satisfy all the equations simultaneously, right? So for 2 equations and 2 variables, here are the possible pictures we can have. Let me draw a few of these. So okay, we can have 2 lines intersecting at a single point, right? Or we can have 2 lines intersecting at multiple points. But watch what happens if I try to draw that. All right, here's the blue one. It's intersecting there. I need to also intersect at another point, but all of a sudden I'm intersecting at every single point. All right, so they're really the same line. Or I could be intersecting at no points at all. How do you do that? Well, I just have to draw this one exactly parallel to the green one. So this corresponds to one solution. This one corresponds to infinitely many. The two lines are basically the same line. That's like this one here. These both actually describe the same line. And this one is no solutions. Infinitely many solutions. Okay, really quick, what if we were to add a third equation to the system? So let's say we have a line here and a line here. So yeah, what if we add a third equation? I won't write out an equation. Instead, I'll just graph that equation. It too will be a line. Let's say it looks like that. Okay. So here's my third equation. There's a solution set to my third equation. How many solutions does this system have? Okay. Well, it might look like it has 3 because we have intersection point, intersection point, intersection point. But actually it has no solutions. Why no solutions? Because, remember, the solution to a system of equations has to satisfy all of the equations simultaneously. In other words, it has to lie on all of the lines. So I need a point that lies on all 3 of these lines. And if you think about that for a bit, you realize that you can't find such a point. What would it look like if a point lied on all 3 of the lines? Well, I'll draw a green one and a blue one. And now I have to be really careful when I draw the red one. It has to actually go through that same point of intersection. So here's an example of 3 solutions, 3 equations, 1 solution. Okay, great. Let's go to 3 variables. So let's do an example with 3 equations and 3 unknowns. Okay. Oh, by the way, is it possible for a system of 2 equations like this and 2 variables? Is it possible for something like this to have exactly 2 solutions? Or exactly 3 solutions? Well, if you follow this geometric argument, then that's clearly not possible, right? Because you can't have 2 lines intersecting in exactly 2 points, right? As soon as you intersect at 2 points, you intersect at all the points. Turns out that's a bit harder to prove algebraically, that the only possibilities are 1, no solution, and infinitely many. But you can try to do that if you'd like. But let's move on to 3 equations with 3 unknowns. This gets very tedious, as you've probably experienced. So let's do x. Actually, you know what I want to do? I want to rename my variables. So instead of x, y, and z, let's do x1, x2, and x3. So we'll do x1, x2, x3. Are going to be my 3 variables. I'll write the system down here. So we have x1 minus 3x3 equals -2. And then my second equation will be 3x1 plus x2 minus 2x3 equals 5. And then my third one will be 2x1 plus 2x2 plus x3 equals 4. Okay, so this is my system of 3 equations in 3 variables. Why am I doing x1, x2, x3 instead of x, y, z? Well, I figure, we just did 2 equations. We're now doing 3. Probably next we'll want to do 4 equations, and we're at the end of the alphabet if we do x, y, z. So this will generalize easier to multiple equations. Okay, what's our plan here? Can we make a plan? Let's try the same idea as before. So this idea of elimination actually is going to work really well. So here's what I'm going to do. I'm going to try to eliminate x1. So here's the idea. So first step, let's say, eliminate x1 in the second equation. And while we're at it, why don't we eliminate it in the third equation as well by subtracting a multiple of the first equation. Okay. What multiple should we choose? Well, we should choose, we should try to get this same coefficient here. Right? So we have 3x1. Let's multiply the first equation by 3. So I'm just going to write that over here. 3x1 minus, this can become a 9, isn't it? 9x3 equals -2. And you know what? I know I'm going to confuse myself because there's no x2 in the first equation, but there is in the second. So I'm just going to write a 0x2. And then I have a minus 9x3 equals -6. Remember to multiply that side also. Okay. Now we're going to actually, yeah, let's put the second one up here. So I have 1x2 minus 2x3. Okay. I'm taking my second equation and I'm going to subtract this one. This one right down here is 3 times the first equation. What do I get? So I'm subtracting these two equations. I get 0x1, that's what I wanted, right? But I have 1x2 minus 0x2, that's a 1x2, so just x2. And then here I have to be careful, 2x3 minus -9x3, that's going to be a plus 7x3. And I have 5 minus -6, that's going to be an 11. Okay, so I'm going to write my system of equations out here again. Let me just put a 0x2 minus 3x3 equals -2. That's my new second equation. x2 plus 7x3 equals 11. What's my new third equation? Let's also do the same trick. So I'm going to take my third equation. I'm just going to write it down here. It's x3 equals 4. And I'm going to subtract an appropriate multiple of this first one. What multiple should I choose? I should choose 2, right? Because I want to get this to be a 2. So 2x1 minus 6x3 equals... again, confuse myself again. I just know it. So I'm just going to write in my 0x2. And now I have a minus 6x3 equals -4, right? And I'm subtracting this. So again, these cancel. The x1s cancel. And now I have 2x2 minus 0x2, that's 2x2. x3 minus -6x3 is a plus 7x3. Finally, 4 minus -4. You have to be careful there, right? I think it's 8, not 0. Okay, so there's my new second equation. Or my new third equation, I'm sorry. Okay, great, beautiful. There's my new system of equations. Different from the first one, right? But it has the same solutions. I didn't do anything to the solutions, right? Because I'm taking this equation, true equation, and I'm subtracting the same thing from both sides, right? Because this equals that. Okay, let's keep going. But what do we do next? So we've eliminated x1 in both of these. Can we eliminate x2? Well, we can't eliminate x2 in this one without reintroducing the x1. So the next idea, this is the second step, is going to be, we're going to try to eliminate x2 in the third equation by using the second one. So we're going to eliminate x2 in the third equation by subtracting a multiple of the second. subtracting or adding. Doesn't matter how you think about it. Multiple of the second. What multiple of the second equation should we use? Well, we want this to be 2x2. So I should multiply the second equation by 2. I'm going to do that right here. So I get 2x2 plus 14x3 equals 22. And I'm going to subtract that from the third equation. And then whatever I get, that will be my new third equation. Okay, so subtract. These go away, these cancel. I have 7x3 minus 14x3, that's negative 7x3. 8 minus 22 is negative 14, I think. Okay, and that's my new third equation. So here's what I have. x1 plus 0x2 minus 3x3 is negative 2. My second equation looks like this. And my third equation now looks like this. This is actually known as a triangular form of a system of equations. Or this is called a triangular system. This is a triangular form. Well, it should be obvious why we use the word triangular, right? It kind of looks like a triangle. But this is useful because we can almost immediately write down the solutions now. So the idea is x3 is, well, negative 7 x3 is negative 14. That means x3 is 2. What about x2? We're kind of going up one equation now. So x3 is 2. This equation only has x2 and x3 in it. So x2 is 11 minus 7 times x3, okay, which is negative 3. Now we know x3 and x2, so we can go back up to the first equation. x1 is negative 2 plus 3 times x3, which is 2, which ends up being 4. So our solution is x1, x2, x3 equals, what do we got? 4, negative 3, 2. Okay. All right. So I wasn't going to talk about matrices today at all, but I sort of changed my mind halfway through this. But all I want to show you actually is how what we just did is it was a little bit messy, right? How we organized it. First of all, it was annoying to have to keep writing down x1, x2, x3, right? Must have written that down about 50 times. But all that we really cared about were these coefficients, right? And so here's what I'm going to do. I'm just going to write down the coefficients. So here's my coefficient of x1. Here's my coefficient of x2. What am I going to write? I'm going to write a 0, right, because there's no x2. And my coefficient of x3 is a negative 3. Let's do that with the second one. So I have 3, 1, and negative 2. And then I have 2 x1 plus 2 x2 plus 1 x3. And let's go ahead and write down these numbers. Negative 2, 5, and 4. Maybe let's make a little bar separating them from the rest. And also going to put some brackets around. Okay. This is really what's important for solving the system. Okay, and this is called the augmented matrix of the system. A matrix is just an array of numbers. This is called an augmented matrix because I'm also sort of tacking on this right side here. And so let's try to retrace our steps by using the matrix. Okay, so let's copy on this matrix again here. What did we do in this step? What we did is we took our second equation, the second row, and we subtracted a multiple of the first equation to eliminate the x1. So in other words, we tried to make that 3 a 0. Tried to cancel out all the x1s. And so I'm going to take my second row. I'm going to write down my first row as is. I'm going to take my second row and I'm going to subtract 3 times the first row. Okay, that's subtracting 3 times the first equation. So 3 minus 3 is 0. 1 minus 0 is 1. Now I have minus 2 minus, this is now negative 9, right? So that becomes a 7. Same thing here. 5 minus 3 times negative 2. Okay, which is 5 minus negative 6 is positive 11. And then we do the same thing here. I'm taking this row, subtracting 2 times this row. 2 minus 2 is 0. 2 minus 0 is 0. 1 minus 2 times negative 3, right? I'm taking 2 times this row. Basically just doing the same thing as over here, right? So 1 minus negative 6 is, again, a 7, I guess. Oh, sorry, I messed up. 2 minus 0 is not 0. Right? 2 minus 0 is 2. And then we have 4 minus 2 times negative 2, right? Which ends up being 8. Okay, then we do the same thing again. But our goal has shifted slightly. We now want to get rid of this x2 in the third equation. In other words, we want to turn that 2 right there into a 0. So I'm actually going to write down the first 2 rows. And now I'm going to subtract 2 times the second row from the third row. So I have 2 minus 2 is 0. 0 minus 0 is 0. And 7 minus 14 is negative 7. 8 minus 2 times 11, that's 22, is negative 14. Okay? And then from here, what we can actually do is just write this out again. And then we get what x3 is, we get what x2 is, and then we get what x1 is in that order. So this is already sort of showing maybe the utility of keeping track of the coefficients of our equation in a matrix. Okay, I had to write down a lot less over here. And we can kind of do things mentally also. But we're going to talk more about this later. What I just did here was a special case of what's known as Gaussian elimination. Okay. That'll be the topic of the next lecture. What else would I like to talk about today? Let's talk about geometry really quick. So, geometry. So we talked about what does a solution to ax plus by equals c look like? What about the equations that we just wrote down in 3 variables? So the solution set of something that looks like ax plus by plus cz equals d. What is that kind of object? Well, it's a plane. So it's a 2-dimensional object. It's a plane, but it lives in what space? I have 3 variables, right? So it lives in 3-dimensional space. Okay. And what is the solution to the system? It's the common intersection. Not of lines this time, but of planes. Of all the planes. Okay? So in this case, we have 3 planes in 3-dimensional space. And it just so happens that they all intersect at that point and no other. Okay, that's what we just found. Okay, as you can imagine, it's going to start getting more and more complicated to visualize these things. So actually, I drew a little picture of some of the possibilities that we can have. So let's take a look at these. So this first one here, we have 3 planes intersecting at 1 point. You see that point? It's just this one right here in the middle. So the red one and the green one actually intersect along an entire line, but then if we also want to intersect with the purple one, we're just intersecting at that 1 point there. So this picture is actually very much like the problem we just did. What about this one here? Here we have all three intersecting actually in a line. Okay, so there are infinitely many solutions here. Infinitely many solutions. That's what this line is. It's the solutions. But the interesting thing here is actually that we have infinitely many solutions, but three totally different planes. Right? So you can actually have infinitely many solutions without any equation just being a multiple of the other. Like, remember back here, the only way to get infinitely many solutions with two equations and two variables is just in a boring way. One equation is a multiple of the other, so it's actually the same line. We can get more interesting examples here. What about this one? We just have three parallel planes, no solutions, right? No intersection points. This one, how many solutions do we have here? Well, again, it's no solutions, right? Because even though this one intersects this one along a line, and so does this one, there's no point where all three planes intersect, right? Because the red one and the purple one just never intersect. So there are no solutions. Okay. This one, it's hard to see, but all it's basically the same plane three times. That's what I was trying to get at here. And so that can happen, right? And you can have the same plane three times. How many solutions does that have? Well, infinitely many. And here the solutions actually form an entire plane, not just a line. And what about this one? What do you think about this one? How many solutions does this system have? Well, this one again is no solutions because the red one and the purple one intersect here, but the green one doesn't. Okay. I mean, you could say maybe, you have to keep in mind these planes continue going on in every direction. So, maybe if you go far back enough, these actually do sort of collapse down and meet up at one point. But yeah, you can definitely have a configuration that looks like this where you have no solutions. So already in 3 dimensions is getting quite a lot more interesting. Let me give you a quick problem to try. So along the way, throughout these lectures, I'm going to include some problems along the way. And what I'd encourage you to do is, as soon as I give you the problem, to pause the video and think about it. So none of them will be terribly difficult, but it's just something to be good to think about during the lecture, sort of just to see if you're understanding the most important ideas. Okay, so let's suppose we have a system of 2 equations in 3 unknowns. Okay, there's 3 variables, but only 2 equations. Okay, so here's my question. Can such a system have exactly 1 solution? Okay, so you can take a bit of time to think about that, and the hint is to think geometrically. Okay, so hopefully you've had some time to think about this. So, what is this geometrically? We have 3 unknowns. What does that mean? That means that, our solution space is, our solutions are living in 3-dimensional space. Okay, so this is 3D space. We have X, Y, and Z, for example. But we only have 2 equations, so we only have 2 planes. Okay. Can 2 planes, this is the new question, okay? So i.e., can 2 planes intersect at exactly 1 point? And I think that's a really helpful thing to I think it's really helpful to try to think about that. Try to visualize two planes intersecting at one point, and see if you can convince yourself that that's either possible or impossible. Turns out it's impossible, but I'd encourage you to try to visualize that. Okay. The point is, we can actually we can deduce certain things about systems of equations without even seeing the equations. Right? We can just use geometry. Okay. One final example. So let's do a let's talk about a parametric description of the solutions. Parametric description of solutions. Okay. So sometimes we have infinitely many solutions, but we still want to describe them, right? So how can we describe them? Here's an example. Okay, 2x1 minus x2 plus 5x3 minus x4 equals negative 30. Yes, I have 4 variables. And then my second equation, I'll put a really nice one. x3 plus x4 equals negative 6. So there's my system of equations. And notice that, so yes, this is a system with 4 variables, but 2 of the variables have already been eliminated from the second equation. Okay, what should we try to do now? First of all, the solutions are living in 4-dimensional space, right? Each of these equations represents some kind of 3-dimensional object in 4-dimensional space. Very tough to visualize. But we want to somehow look at the intersection of these two objects. Okay, let's try to eliminate x3 from this equation by, I guess if we take 1/5 of the first equation, then we'll turn that 5 into a 1. And then if we subtract 1/5 of this equation from this one, do you see what's going to happen if we do that? So, yeah, maybe I won't even write it out because you see what's going to happen. We're going to reintroduce, so we will eliminate x3, which is great, but we're going to reintroduce x1 and x2, which we don't want to do at all. Right? That will just make it more complicated. So basically we've made all the progress we can with the second equation. We can't get this down any further. Okay. And so what can we do? Well, we still don't know what x3 and x4 are, but it turns out we can actually freely choose one of them. So let's suppose x4 is, I'll just call it any number I want. So let's say it's t. Well, then what is x3? And x3 is just minus t minus 6. Right? Okay. So once we determine x4, we know what x3 has to be. Let's try to plug this into the first one. So what about x1 and x2? So our first one becomes 2x1 minus x2 plus 5 times x3, but x3 is minus t minus 6. And I have minus x4, which is t. And that equals 30. All right, let's simplify this a bit. So 2x1 minus x2. How many t's do I have? I have minus 6t, I think. And then I have a minus 30. And that equals minus 30. Okay, I can get rid of the minus 30s. Minus 6t equals 0. All right, so there is my, there's what I have left. So what is x1 and x2 in terms of t? Well, I mean, if I try to solve for x2, I get something in terms of x1, right? And if I try to solve for x1, I get something in terms of x2. So it turns out that we have another free choice here. Okay. So let's make a free choice of x2. So I'm going to let x2 equal some other number. Okay. It's any number. T is any number. S is any other number. It doesn't have anything to do with T. You can choose something completely different. Well, then in that case, now we can solve for x1, right? So 2x1 equals, well, it's s plus 6t, right? So x1 is 1/2 s plus 3t. Okay, great. So I'm going to write down the solution that we just found. So the solution is x1, x2, x3, x4 equals, what is x1? x1 is 1/2 s plus 3t. x2 is s. x3 is minus t minus 6, and x4 is t. And you can actually test this out. Like if you plug this into these equations, everything just ends up canceling out. You get a true statement. You get 0 equals 0 on both sides. Okay, well, what is s and t? So where s and t are literally any numbers. Okay. Great. Okay. One last question for you. Is this system consistent or inconsistent? Okay. Do you remember that definition? So a system is consistent if it has at least one solution. Does this have at least one solution? Sure does, right? It has infinitely many solutions, right? Because we can pick any values of s and t and get a solution. So yes, this is consistent. So let's write that down. This is consistent. Okay, and this right here is called a parametric description of the solution. Okay, s and t are the parameters, and I can choose any values of those parameters I want and get a solution. Okay, so what we see here is that even if we have infinitely many solutions, we can still describe them algebraically. And so in the next lecture, we're going to talk about a sort of general method to solve systems of linear equations, any number of linear equations and any number of variables, and describe the solution set, okay, with parameters like this. Okay, thanks for watching.